Good afternoon. I'm Kai Zhang from the CASK Laboratory of Safety at Institute of Computing Technology, Chinese Academy of Sciences. I'm delighted to share our work today, LoRaC, combining points with large language model for robust sequential recommendation. I'll introduce our work from the following four aspects. First, I'll introduce the background of our work. Recommender systems are indispensable tools in our daily life, helping us select information from massive amounts of data. However, their inherent openness makes them vulnerable to poison attack. In such attacks, attacker typically inject series of fake users to manipulate icon recommendation, achieving some malicious goals such as promoting some items or damage overall performance of a recommender. An existing defense method against such attack can be categorized in two types. The first type is adversarial training. These methods typically follow a min-max paradigm, which introduce the adversary perturbation at the parameter level to ensure the recommendation performance in the worst-case scenarios. However, this method often assumes the attack severely impairs the overall performance of the recommender. In reality, some poison attacks such as item promotion may not affect the recommendation quality for all users. So, this leads to possibility that adversarial training may not always be effective. Another type of method is detection. Detection-based method aims to directly identify and remove potential fraudsters. This detection mechanism often incorporates specific assumptions such as unpredictability of fraud's behavior or rely on supervised data. Therefore, the performance of this method is limited by their reliance on the heuristic priors or supervised data. In the real world, as attacks vary, the ability of defense method to generalize to diverse attack is vital. However, existing methods often learn specific patterns from the prior knowledge, making them ineffective against some attack divided from the learned patterns. So, how do we learn a more general pattern for better defense? Recently, lots of studies have shown that large language models have strong generalizability and can aid various attacks in achieving improved generalization. So, in our work, we proposed to utilizing large language models' open world knowledge to enhance defense by generalizing from specific to general patterns. So, based on the above ideas, we propose LoRaC, a general and adaptable framework which consists of two primary components. The first component is sequential recommender system. It can be any existing sequential recommendation model. And the second component is multi-component, is the large language model enhanced calibrator. It dynamically calibrates user weights during the sequential IS training with the large language model. It aims to lower the fraudulent training weights to mitigate their impact on the system. And so first, I will give the formal definition of the sequential IS within our framework, just as a preliminary. We can break down the sequential IS in two parts. The first part is feature encoding. In this part, we can use the modality-specific encoders to transform the item style information to low-dimensional embedding, just like E. And in the second part is sequential recommendation. In this part, based on the embedding we just obtained, we can use a sequential model to make sequential prediction and to get the predictive embedding E prime. And finally, we can use the dot product of the item original embedding and the predictive counterpart to get the prediction score, right? And the next part is large language model enhanced calibrate. Just as I said before, it calibrates user weight during the sequential IS training to mitigate the impact of the fraudster. And to accurately and effectively filter out the fraudsters, LCT use two types of knowledge. The first type is specific knowledge from the current recommender. It highlights the detailed differences between the genuine users and fraudsters. And second type is open world knowledge from the large language model. It provides the LCT with a broad understanding, enhancing its ability to generalize across different types of fraudsters. And I will introduce how we model specific knowledge in this stage. For each item in the user historic interaction list, we concatenate each two types of embedding. The first type is original embedding from the modality specific encoder, and the second type is its predictive counterpart E prime from the sequential model, and we can get a list of the representation K, and then we can use the self-attention to summarize the features and to get the representation RU. And finally, we can use the two-layer perceptron to map the RU to the PU, which reflects the likelihood of the user being a fraudster. And after modeling specific knowledge, we aim to integrate the open knowledge from the large language model. So we construct several prompts about whether the given user is a fraudster. Specifically, we specify the recommendation scenarios, that is the recommendation context, for example, the news recommendation, and then we encode a user's historic interaction sequence is as follows. So like item 1 with the features, item 2, and so on to item n. And finally, we provide the instruction, please assess the likelihood of the user being a fraudster. And then we feed this prompt into a large language model to get the low-dimensional embedding LU about the fraudsters. And then we can maximize the agreement between the two types of knowledge to integrate the open world knowledge into the specific knowledge, just like we maximize similarity between the LU and RU. And RU is we obtain in the specific knowledge modeling stage. And then after modeling two types of knowledge, we proceed to train the LCT. We first establish a set of known fraudster user and the supervised dataset named UAttack. The first part loss is detection loss. We label the user in UAttack as 1 and the user in original user set U as 0. And as we will know, as we mentioned before, there may be some potential fraudsters in the original user set. But we treat them as genuine user in the first detection loss. So we do not want the LCT to predict the p-values for users in the original set as 0. So we add the entropy regularization loss to avoid extreme predictions. And the final part is the large language model enhanced loss. It integrates open world knowledge about fraudsters. And the likelihood obtained through the above loss function can be considered as approximated likelihood, because we just treat some potential fraudsters as genuine user in the first detection loss. So a straightforward method to do the calibration is use such the approximated loss as a user training weight, just as shown on screen. So however, as we mentioned before, the original user set U may consist of both genuine users and the potential fraudsters, leading unstable calibration, just like some overlap is in the p-values and the p-values, the distribution of the p-values changed logically about the fraudster AUF. So how do we use this approximated likelihood to calibrate user weights? To answer this question, we further proposed an iterative weight update mechanism. First, we observe that well-trained classifier often display a skew logic distribution, sometimes refers to overconfidence. So specifically for users in UN, the logic distribution of PU skew towards 0, while for users in UF, the logic distribution varies depending on different scenarios, such as different hyperparameter, different training epochs, or different attacks, and so on. In other words, a well-trained LCT may have some capability to distinguish these two types of users, reflecting some different logic distribution or with different mean value, different values, and so on. So we can use such capability to set an adaptive threshold to filter on certain fraudsters. In our paper, we use mu-O, that is the mean value of PU across the original user set as an adaptive threshold. And furthermore, we established a weight pool to tracking per user's weight coefficient Xi. And after reaching certain training epochs with LCT, Xi is updated as follows. We just lower the weight coefficient for user whose p-value greater than mu-O and distributes the decreased values to other users uniformly. And in our paper, we prove that this update mechanism can guarantee that the expectation of weight coefficient for genuine user increase, while the expectation for potential fraudsters decrease with each iteration. And finally, we can calculate user weights as just shown on screen, and the calibrated loss is also shown on screen. By continuously reducing the training weight of the fraudster, we can mitigate their impact on the system. And then next part is we examine the performance of the LoRack. These are experimental setup of our work. And then the first is the robustness against poison attacks. We find that the LoRack reduces the average target item hit ratio by 75% and the average target NDCG by 87%. That is, the LoRack significantly reduces the attack success ratio. And then we use the backbone model on the clean dataset as a baseline to evaluate the ability of defense method to maintain the recommendation performance. We found LoRack achieves the best result, that the LoRack can maintain the recommendation performance. And then we also conduct ablation study to evaluate each component of the LoRack. We found that each component plays a vital role in ensuring robust recommendation, and specifically the open world knowledge from the large language model helps counter unknown attacks. That is the DP attack in the screen figures. So. And feedback from the sequential recommender enhances the precision detection. And we also analyze the large language model size. As the size of large language model increases, there is a general trend towards enhanced defensibility against poison attack in LoRack. And finally, we also evaluate the generality of LoRack. We evaluate the promotion attack against the extremely popular items, and we evaluate different background model, different modality of the sequential recommender system. We found that the LoRack consistently achieves the best defense result, defense performance. In a nutshell, we pioneer exploration of the large language models knowledge in defense. We found that large language models knowledge helps improve the generalizability of the defense method against different attacks. And as the large language model size increases in size, the ability to enhance defense capability gradually improves. And then we propose a general adaptive framework, LoRack. LoRack effectively reduces the successful ratio of attacks. And the interactive weight calibration we proposed provides enhanced robustness while maintaining the recommendation performance. And finally, I'd like to thank for all authors contribute to our paper. And that concludes my presentation. And welcome for questions, and I'm looking forward to engage with you. And these are references in our paper, in our slides. That's all. Thank you very much.
Thank you very much.